So they want to know how much momentum a golf ball would have to get to this height above the surface of the moon, launched from the surface of the moon. I think my plan is I'll find out how fast it's got to be going at the surface of the moon to get up that high, using conservation of energy, and then I'll just use the definition of momentum. Whatever that speed is, I'll multiply it by the mass of the golf ball to get the magnitude of the momentum, and I'll call the direction upward and have the question answered. So I'm going to use conservation of energy to get an idea of how fast it's got to be going. You know, we're talking speed and position, and the concept you usually use in problems involving speed and position is conservation of energy. So here's my before picture. This is the moon. I'll give it a radius r. And I copied down some values from a previous problem, the one right before problem number 4. And we need these two, the radius of the moon and the mass of the moon. So radius 1.74 times 10 to the 6. Meters. The mass, I'll use the symbol capital M for the mass of the moon, and it's given as 7.35 times 10 to the 22 kilograms. Here's my little golf ball. I launch it up here with some velocity v, which is what I'm looking for. It's got a mass of 45.9 grams, or 0.0459 kilograms. Okay, it goes up to some max height h, which is given 942 kilometers. I'm going to call that 0.942 times 10 to the 6 meters. Have it same kind of units, same power of 10 in terms of meters as their radius of the moon. This is still r. I'll call this r prime, this distance that the golf ball is from the center of the moon in the after picture, where r prime by inspection is just r plus h, which is 1.74 megameters. I'll still write it as times 10 to the 6 meters plus 0.942. .942 times 10 to the 6 meters. Alright, so r prime, that adds up to 2.682 times 10 to the 6 meters. R prime is just 2.682 times 10 to the 6 meters. Okay, I think we're ready. This is supposed to be right at the surface. This where the golf ball is up high. I think we're ready to apply conservation of energy. Let's try it, see if we're missing anything. E is equal to E prime. As the energy in the before picture is equal to the energy in the after picture. Consists of kinetic energy plus gravitational potential energy. And same thing over here in the after picture. K prime plus UG prime. Except in the after picture, I didn't write that down, but V prime is equal to 0. So there is no energy of motion. The kinetic energy is 0. Over here we got 1/2 mv squared plus capital G, Newton's universal law of gravitation constant, gravitational constant, m for the mass of the moon, m the mass of the particle over r their separation, the separations of their centers, in particular the distance the golf ball is from the center of the moon, except with a minus. And then over here we got 0 minus, same thing, except for the separation of the centers is the separation in the after picture. Okay, I just have to solve that for v now. Then I'll multiply the result by lowercase m. It's easier to solve for v than it is to solve for lowercase m, especially since, to solve for mv. The lowercase m just cancels out because it's in every term, so I divide both sides by lowercase m. I got a 1. M over m is 1 every place, and whatever it's multiplying is just becomes what it was. 1 times anything is itself. So long way of saying that the m's cancel. So I got 1/2 mv squared. I'm going to add gm over r to both sides. On this side I get a 0, and on the other side I'll just have to copy it down. G capital M over R minus G capital M over R prime. I think I'll factor this G capital M out on both sides, on the right. It occurs in both terms on the right, so I got 1 over R minus 1 over R prime. Multiply both sides by 2 and take the square root. I get this expression for the speed with which the golf ball has to be launched straight upward in order to achieve the given height. So let's plug in values here. V is going to be equal to square root of 2. Capital G is 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. And the mass of the moon was 7.35 times 10 to the 22 kilograms. And then we got 1 over the radius of the moon in this case, which we had as 1.74 times 10 to the 6 meters. And then minus, our prime was 2.682 times 10 to the 6. Meters. Alright. Take the square root of all that, and I get for the speed 1407. And you should work out the meters per second. Let's make sure that they do. So the newtons inside the square root, it's a kilogram meter per second squared. And let's work on the kilograms first. I got kilograms times kilograms divided by kilograms squared, so that yields just 1. Meters times meters squared, that's meters cubed, divided by meters. I'm going to wind up with meters squared up there. Meters cubed divided by meters is meters squared. And then the second squared, there's nothing that cancels that out, and that's all we got. So meters squared per second squared inside the square root. That gives me, when I take the square root of that, I've just got meters per second, which is good. That's what we wanted. And then I'll calculate the magnitude of the momentum is just the mass of the golf ball times the speed, which was 0.0459 kilograms. And then times the speed we just calculated, 1407 meters per second. So the momentum in magnitude is just 64.57 kilogram meters per second. And then I think it's all 3 sig figs up here, so we'll quote our result to 3 sig figs. Call it the momentum vector, which is what I'm looking for, is 64. That's how much momentum, so it's probably okay to give the magnitude, but certainly alright to give as the final answer the magnitude and direction of the momentum that you have to give the golf ball in order to make it leave the surface of the moon and rise up to a height of 0.942 times 10 to the 6 meters above the surface. So we'll say it's that magnitude, rounded that value, and then upward for the direction. And that's the answer.